Welcome viewers to the third segment of the first lecture for the course of linear algebra. We start this third segment with a proposition 1. Let me state it first, then I will prove it. Let AB be n times n matrices if both of these matrices are invertible so is their product AB, and the inverse of AB is equal to the inverse of B times the inverse of A. Okay. More generally, if A1 all the way up to AM are invertible, then so is the product A1 times all the way up to AM, and its inverse is AM inverse all the way up to A1 inverse. Okay. So this is our proposition. So let us try to prove it. Assume that A and B are invertible. Okay. We check that the inverse of AB is B inverse times A inverse, right? So this means that we have to check if the inverse of AB is indeed B inverse times A inverse. Okay, so we just use the definition of inverse. So we put AB first, and then we put this B inverse times A inverse, and then see if we get the identity matrix back. Okay, now use the associativity law of matrix multiplication and group B and B inverse together, and this is nothing but the identity matrix, and the identity matrix multiplied with A inverse will give A inverse back, and the result of multiplying A with A inverse is going to be I. Okay, again we check that B inverse times A inverse times AB is equal to B inverse times, we group A inverse and A first to have B inverse I, B, and the multiplication of I with B results in just B, and the multiplication of B inverse with B is just I. So this way we check that B inverse A inverse is indeed the inverse of AB. In other words, we have proved this. Okay. Now, for the last assertion, we use the method of induction. Okay, for the last assertion, we will be using induction. Okay, so okay, so when m is equal to 1, the assertion holds trivially, meaning that the inverse of a1 is simply a1 to the minus 1 or a1 inverse. Okay. It asserts that the inverse of a1 is simply the the inverse of a1. This holds trivially, right? This holds trivially. Next, we assume that the assertion holds for m equal to k, right? Then we have to show that it also holds for m equal to k plus 1. Holds for m equal to k plus 1. Okay, so we start with the hypothesis of this last step. We suppose that a1, a2, all the way up to a k plus 1 are invertible n times n matrices. Okay, so we take k plus 1 invertible matrices, invertible n plus n times n matrices. Okay, and we can always do that because the matrices that we have a1 all the way up to am are all invertible, right? And we denote by p the product of the first k matrices. Okay? So 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 there are k plus 1 matrices here. We forget the last matrix and take the first k matrices, okay, and denote their product by p. That is, p is equal to a1, a2, all the way up to ak. This is our equation number 6. I need some room and hence I erase this part. Okay, and its inverse inverse is ak to the minus 1 all the way up to a1 to the minus 1. So it's the assumption from the assumption. This is our equation number 7. Okay. Also, we know that a sub k plus 1 is invertible, right? A k plus 1 is invertible. Therefore, B, see that, therefore, using the result that we have proved in the beginning, we have proved that AB to the, the inverse of AB is B inverse times A inverse, right? So using this result, we can write that P times A sub k plus 1 is going to be invertible as well, and the inverse of this resulting matrix is given by ak plus 1 inverse P inverse, which means the inverse of a1 ak plus 1 is going to be equal to ak plus 1, the inverse of ak plus 1 times the inverse of ak all the way up to the inverse of a1. Okay, this is what we can do using 6 and 7, right? So this completes the proof using induction, QED. Okay, so the last thing that we want to do for the first lecture is block multiplication. Block multiplication. Okay, so we can decompose matrices into blocks to facilitate the given matrix multiplication. Okay, so to illustrate that, let us have two matrices, M and M prime, be matrices, and M, big M, is of size M times N, and big M prime is of size N times P, meaning that we can form the product M times M prime, which will be a matrix of size M times P. Okay? Also assume that R is an integer less than N. Okay? And we want it to be greater than 1 or equal to 1. Okay? Now, we can decompose M and M prime in the following way. So, we write M as two blocks, A and B. Okay? And M prime as two blocks, A prime and B prime. Okay, so we decompose each of the two constituent matrices M and M prime in such a way that A has R number of columns. So there are R columns here, and we also want A prime to have R rows, and that's it. And then we can write M times M prime as A times A prime plus B times B prime. Okay, using matrix multiplication law, you should be able to verify that it can always be done. Okay. Okay, so let me give you an example of the use of this block multiplication rule. Let us choose M to be 105, 017. This is our M, and our M prime is going to be this 3 times 2 matrix, 2, 3, 4, 8, 0, 0. Okay. So here this is 2 times 3 matrix, and this is a 3 times 2 matrix. Okay, so now I choose R to be 2 now, right? Because our N in this case is 3, I have to choose a number which is less than 3, an integer less than 3, and I choose R to be 2, so that the block is something like this here, and this block has to be placed here, because this guy is our A and this is our A prime. All we want is that the number of A, the column number of A should be the same as the row number of A prime. So if we choose the partition here, then we are good. Okay, so and we can check that well, according to the rule of block multiplication, it is going to be 1001 times the 2 times 2 matrix 2, 3, 4, 8 plus 5, 7, a column vector, times the row vector 0, 0. Okay, so this is an this is 2 times 2 identity matrix, so this is simply 2, 3, 4, 8, and we get a 2 times 2 0 matrix, right? So what we have finally is 2, 3, 4, 8. So using ordinary multiplication, you check that you indeed get this 2 times 2 matrix. Okay, now let me erase everything. We may also multiply matrices divided into blocks. Divided into more blocks. So we just used 2 blocks in the previous example, but we can have more blocks. For our purposes, a decomposition into 4 blocks will be the most useful. decomposition into 4 blocks. Okay, let's see how we do that. So we need R plus S to be N in order to do that. Okay, um, so we start with two matrices, M, which is of size M times N. Okay, so the number of rows in this matrix is M and the number of columns is N, and we put it in the following block form. There are 4 blocks now, A, B, C and D. Okay, and so the summed R and S of N means that there are number of columns in this partition and there are S number of columns here. Okay, and we have M prime. We also divide it into 4 blocks. A prime, B prime, C prime, D prime, so, and it has to be divided in such a way. We have to create the 4 blocks here in M prime in such a way that we have R rows in this partition. In the top partition we should have R rows. In the bottom partition we should have S number of rows. Okay, so that's the requirement. Okay, for convenience we can call the number of rows here in the left partition we had R number of columns here for M. In the right partition we had S number of columns. For convenience we can write, it's not necessary, the K number of rows here. On the top partition here we have K number of rows and L number of rows at the bottom partition. Okay, so that we have K plus L to be M, since the size of this matrix is M times N. But KL doesn't have anything to do with this construction. Okay, so the result states that M times M prime obeys the 2 times 2 matrix multiplication rule. Okay, so that there will be 4 blocks. The first block is going to be AA prime plus AC prime. You see that both AA prime and AC prime makes sense, since the number of columns of A is the same of, sorry, I think I made a mistake here, AA prime times plus B times C prime. Okay, just the 2 times 2 matrix multiplication. And it makes sense since the number of columns of A is the same as the number of rows of A prime. So that A times A prime is going to be a matrix, a well-defined matrix. And and BC prime makes sense since the number of columns for B is going to be the number of rows in C prime, which is S, right? So here we are going to have AB prime plus BD prime. Here we are going to have CA prime plus CC prime. Finally, we have DB prime plus DD prime. Here, just check that the number of columns of D is the same as I think I made a mistake again. This is good. CA prime plus this is going to be CA prime DC prime, and this is CB prime, and this is DD prime, CB prime, right? So let me quickly check AA prime, BC prime, and AB prime, BD prime. It's good. Then CA prime, DC prime, and we have CB prime and DD prime. Okay, so let's check that this makes sense because number of columns of C is R, and the number of B prime should be R as well, yes, and the number of column of D is S, and the number of D prime should be S as well. The number of rows in D prime is S as well. Okay, so they make sense. So this is how you do the matrix multiplication for 4 blocks of matrices. Okay, let me give you an example finally. Example. Suppose we have 2 times 3 matrix 1 0 5 0 1 7. This is the first matrix, and we have a second matrix 2 3 1 1 4 1 0 0 0 1 1 0. This is a 3 times 4 matrix. Okay, so let us take in this example. So so this is a 2 times 3 matrix, and this is a 3 times 4 matrix. Okay, so in this case n is 3, this number n is 3, and we have to write n as r plus s. We choose in this case r to be 2 and s to be 1. Okay, so okay, I want to erase it. Okay, so this is, so just the column number I can write it as, so this is going to be our partition. So this is 2 plus 1, and this is going to be the other partition, right? This is also 2 plus 1, right? This partition. Okay, so this thing is quite arbitrary, so I make this guy be like this, and this thing to be like this, to have 4 blocks. Okay, so now according to the block multiplication rule, it is going to be a matrix with 4 blocks. Okay, so this block we are going to get by this operation, right? 1 0 gets multiplied with this 2 times 2 matrix, 2 3 4 1, and 5 is going to get multiplied with 0 1. Okay, so this you see that is going to be just 2 here. The first entry is 2. This is going to be a row vector only with 2 columns. So this is going to be 2, and this is going to be 3, and this is going to be 0 5. So that finally we have 2 8, right? So this block is 2 8, not 28. This is 2 8. Okay, so similarly we can find this block by doing this calculation. So this is going to be 1 0, then 1 1 0 0 plus 5 times 1 0, right? This is now I have a row vector consisting of 1 0, 1 0 1 0 is 1, and 1 0 1 0 is 1 again, 1 1 plus 5 0, which gives us 6, right? 6 1. So this is going to be 6 1, right? Similarly, you can go on to compute this entry, and this entry is going to be equal to 0 1 getting multiplied with 2 3 4 1, and 7 getting multiplied with 0 1. So the first entry is 4, and the second entry is 1, and that gets added to 0 7, so that you have 4 8, right? Which is 4 8. This block is 4 8. Finally, we need to find this block. So let me do the calculation here. Again, you have 0 1 getting multiplied with 0 1 getting multiplied with 1 1 0 0 plus 7 times 1 0. This gives you a row vector consisting of 2 columns, which is 0 here and 0 here and 0 here, and this is 7 0. Finally you have 7 0. So you have 7 0 here. So this is the matrix that we were looking for. So by usual matrix multiplication, you should be able to find this matrix as well. Okay, so this way we have an example of block multiplication for the case of 4 blocks. Now there is a question. The question is, instead of having the partition here, if we had the partition here, would we get the same result? We should, right? Let's check. Let's verify if we get the same result. Okay, so let me erase everything. So we do the same example 1 0 with a slightly different partition. So for the first matrix we use the same blocks, but for the second matrix we use slightly different blocks. 2 3 2 3 1 1 4 1 0 0 and 0 1 1 0. So we do the blocking in the following way. We cannot change this partition, okay? It has to be the same as before, because this is 2 plus 1 and this has to be 2 plus 1. Okay, so now we use these blocks, and then again we'll have 4 blocks. Let's see what we get for the first one here. We 1 0 gets multiplied with this 2 times 3 block, 2 3 1 4 1 0, and that gets added to this row vector 0 1 1. What do we get? We get 2, then we get 3, then we get 1, right? Plus 5 0 1 1. So we have 2, then we have 8, then we have 6. So we have 2 8 6 here. Okay, for this block we are going to have 1 0 getting multiplied with 1 0, and 5 gets multiplied with 0. So that we have 1 here, and we have 0. We have simply 1. Okay, so for this block we have to multiply 0 1, this row vector, with this block 2 3 1 4 1 0, and 7 gets multiplied with this row vector, right? So that we have a row vector consisting of 3 columns, which is 4 1 0 and another row vector with 3 columns, 0, 7, 7. When we add them, we get 4, 8, 4, 8, 7, right? So here we have 4, 8, 7. Finally, this block we are going to have 0, 1 getting multiplied with 1, 0 and 7 multiplied with 0. So we have 0 plus 0, which is 0. So 0 is here. So this way we check that we get the same result as we did before. So the previous choice of the right partition here. So previously we had this, the right partition, the left and right partition to be this one, right? And for both these choices we get the same final matrix, the final 2 times 4 matrix, which is this one. Okay, so we end the first lecture here. In the next lecture we'll start with row reduction and we'll see how far we can go. So I give you some exercises from Artin's book on algebra. So here are the exercises. One, basic operations, page 31. Okay. 2a, 3, 4, 5. In problem number 5, you have matrices written in this way. Okay. So whenever some entry is missing, it means that that's 0. Okay. So it is the same as this 2 times 2 matrix. Okay. So this is number 5. Then you need to do number 7, number 8, number 11, number 12, number 16, and finally number 19. There are 10 problems here in the first exercise. Okay. So thank you for attending the first lecture.